Okay, moving on here. Known degenerate Matthew Lloyd has a question. Since traditional ideas of faster than light travel seem to be physically impossible, do you think that how's that pronounced? The Alcubierre drives? I've heard the term before. Moving space around a vehicle rather than moving a vehicle through space might be possible. What are the barriers to successfully creating these drives? How do you see us overcoming those barriers? And do you think they will become reality in our lifetime? Do you see better alternatives? Well, that's a whole show. But I could give you the, brief version. Brief version is probably going to be 25 minutes. Let me start this by saying that when we talk about things like warping space and so on, this is a very, very, very good example of the kind of arrogance that we have when we deal with science, and we think that because we see a picture of little grids and lines, here's the rubber sheet, and it's higher in the front and lower in the back, and you can tell because the little grids and lines do this. We think that's reality, but the fact is the reality is infinitely more complex than that. Infinitely more complex than that. I think that our best hope for this kind of thing is this. I don't think it may be, there's a lot of problems with going faster than light, and one of them is it destroys the arrow of time. You can't have the message arrive before the question is asked, or at least some people think so. Certainly the fact that as you get closer to the speed of light, your mass increases, time slows down, and as you get exponentially closer to the speed of light, your mass exponentially goes up until eventually, as you're trying to push through the light barrier, your little mercury capsule weighs as much as the entire universe, or 50 universes. So it's just not possible. The harder you push, the more locked the door gets. And I suspect that is so fundamentally built into at least four-dimensional space, the space that we live in, that doesn't seem likely to be something we can get around. It's another little thing I like to play with, by the way. We talk about living in a three-dimensional world. This is my iPhone cover. And if I asked you how many dimensions this object has, up until recently, I would have said just like you. I said 3 dimensions. Really? Yeah, 3 dimensions. It's got height, it's got depth, and it's got width. Width, depth, and height. And that's what I would have said, and I would have been wrong. This is a 4-dimensional object. It's not a 3-dimensional object. It's a 4-dimensional object, and the 4th dimension is it has height, it has width, it has depth, and it has persistence. It is moving through the 4th dimension along with everything else in this room. But this 4-dimensional object is moving through the 4th dimension of time. I don't know about all the rest of the stuff and imagining the 10th dimension, all the rest of that stuff. I don't know about that, but I'm quite sure about the first 4. This object is a 4-dimensional object, and its motion through the 4th dimension, which is invisible to us, is what gives this object persistence. Because if it didn't have persistence, then it simply would have just disappeared in a flash. But it's here. It was here yesterday, likely to be here tomorrow, and it's got that 4th dimensional quality. So that's just to tee you up and just to get this whole thing with some kind of perspective into here. Just because you can say things like we're going to warp space, we're going to do this, we're going to do that, it's easier said than done. Now, I know these people are physicists, and I know that they have plans to do it, but the closest thing I can think of to an answer for faster than light travel, if it's possible. By the way, I don't know if it was Carl Sagan who said, where Einstein giveth, but he also taketh away, or where Einstein taketh away, he also giveth. Well, relativity says you can't go the speed of light. The closer you get, the heavier you become, the harder it is to push further. He also said that the closer you get, the slower things go. So basically, if you can get going fast enough, you can travel from here to a star in just weeks. For you, back home, everybody's gotten, 4.5 years older, or probably more like 6 or 7. In any event, back to the drive thing. There's a real breakthrough to be made if you've ever seen these things. We had one at the Museum of Science outside the planetarium for 100 years, and I'm sure all of you have seen them. And basically what they are, they're very, very smooth bowls. And they're made out of a very hard plastic. And if you take one of the ball bearings in this hands-on science exhibit and give a little push, It'll go down into the bowl and accelerate on the way down and slow down on the way up and then accelerate on the way down. And looked at from above, it's an orbit. And what you see is this bend, and you realize that the gravity has distorted the space-time. And you see this and you think, oh, I get it, but you don't get it, because that funnel doesn't exist. It's a visualization tool, but it doesn't exist. What's actually happening is, in my understanding anyway, what's happening is, I think what's happening is the area around the fabric of space-time, the matrix of space-time around a high-gravity source gets thinner. And I think that if it's possible to travel faster than light, it's only capable of traveling faster than light as it moves through a vacuum. Now, if you take a beam of light and you shoot it from the air into the water, it actually slows down. That's why the line looks bent by the water. Light is slowing down when it enters the water. The speed of light is slower than it is in the air. And it's somewhat slower in the atmosphere, but the atmosphere is hundreds of times thinner than water. But when light enters the atmosphere from space, from the vacuum of space, it slows down a bit. When it enters water, it slows down a little bit more. So if you think about it, if you had two tunnels that were a really big distance long, from here to the moon, let's say, and you fired off a strobe light, and in one tunnel you had nothing but air, and in the other tunnel you had nothing but water, the light in the air tube would get to the moon faster than the light in the water tube. And if you were living in the water tube, it would appear that light has gone faster than possible. And the only reason it's gone faster than possible is because it's traveling through a less dense medium. And I suspect that's probably where the answer is. If we can find a way to thin out space-time, to make the fabric of space-time thinner, then we will never go faster than the speed of light, but the speed of light will accelerate in that environment. It won't accelerate throughout the universe, but in that little disturbed area, it should be able to go faster. And you say, well, a vacuum, you can't improve on a vacuum. I mean, a vacuum is as empty as it gets. You can't get any emptier than a vacuum. Again, another limitation on our monkey brains, which are astonishing pieces of work. Don't get me wrong. Very, very proud of it. But when we say that there's nothing more empty than a vacuum, this is because we are just seeing things in 3 dimensions and on a large scale. Space has actual structure. There's this quantum soup thing. There is apparently enough energy in a light bulb, in a vacuum, in a light bulb area. Enough energy to power the Earth or the Sun, or some insane amount of energy in the vacuum. How can that be possible? Well, because the quantum states and so on and so on and so on. Well, so that's as far as I know. I don't know what they're planning on doing on warping space, but the idea would be, I think the thing that we could say with some confidence is, whether you want to call it warping space. See, this is where I was trying to go with it. In the diagrams for this, what is it, Albuquerque Drive or whatever, you see there's like a bulge in space-time behind the ship and a dip in space-time below the ship, and the ship essentially goes downhill, and the hill moves with you, and that way, if the hill is moving faster than the speed of light, then you're traveling faster than the speed of light, even though right where you are, the speed of light is not being exceeded. But here's what I'm trying to say about that. When we see that in 4 dimensions, we see the back of space lifted up and the front of space pushed down, the same way as you see it pushed down in the black hole funnel thing and the thing at the Museum of Science. That is a 3-dimensional representation, but that's not it. We're not raising it. We're making it either less dense, or conceivably we could be making it an area where, now that's actually something I hadn't really thought about before. But since 4-dimensional space-time is space-time, it's not space and time, it's all the same thing. It's just one dimension we can't see through. But since space-time is space-time, essentially maybe what it is it's making, I what was the word? It wasn't less dense. Where was I? Just a real... It's thinner anyway. Thinner in front of us, thicker behind us. That's it. If you're making space, or if you're making the vacuum matrix denser behind you, but less dense in front of you, then light should be able to go faster through that less dense area of space-time than it would through a regular vacuum. And whether or not that wave can be propagated at faster than the speed of light, I do not know. Okay, let's